Hello everyone, and welcome to this section on tolerance design. Today we want to be able to explain the concept of tolerancing as a balance between allowed variation around selected targets and production cost. We want to understand that tolerancing is an economic issue for the customer and for the producer, and this has to be decided with a suitable trade-off. We want to be able to calculate the expected tolerance for a characteristic given the component tolerances and understand the concept of natural tolerance limits, or NTLs. Tolerance design, or tolerancing, is the process of determining the allowable variation in a product characteristic around selected targets, so that the product can be produced at a competitive cost while meeting the customer's needs for limited variability. And here we're recognizing that the variability in a part or product characteristic is unavoidable, but should be kept within limits. Now this creates for us an economic problem. For a producer, having lower variability or a tighter tolerance means an increased production cost. For the customer, now, the customer could be, for example, the end user, or it could be the operator in the next assembly line, for example. If the part is moving along to a different production stage, it could be then the people working in that next production stage. Tolerance design then will affect these customers about how the product looks and performs, or how easily it can be assembled in the next higher assembly. It may also determine the length of life or the reliability of a final product, and all of these have economic values for the customer. Therefore, tolerancing is an economic issue for both the customer and for the producer, and a gain for one may result in a loss for the other. Thus, this tolerancing has to be decided by a suitable trade-off. The tolerance provided for a characteristic depends on the manufacturing process by which the characteristic is created. So, in other words, the people, the machines, the environment, the methods. Therefore, tolerancing for a characteristic should be conducted after the final process is selected and finalized. Traditionally, tolerancing has been based on the experience of designers regarding what has worked for them satisfactorily. Experienced designers have documented the tolerances that have worked well for different manufacturing processes. These selections have also been maybe influenced by what tolerance a particular process is capable of achieving. For example, you can find in machine design handbooks. This is an example from the Standard Handbook of Machine Design by Shingley and Mishka, 1986. And here we have examples for the tolerance of drilled holes. So for particular drill sizes, and these are in inches, you have a tolerance of plus or minus, plus 0.007 and minus 0.002 for these given drill sizes. Or for the slightly larger drill sizes, you see that it's plus 0.008 inches to minus 0.002. And in general, these tolerances are calculated as plus or minus 3 standard deviations spread. And this is all, again, under the assumption that our characteristic, for example, drill sizes, follow the normal distribution. Now, these tolerances will be adequate and appropriate to use for a new product if the production machinery used for producing this characteristic has the same capability as those assumed in attaining the standard tolerances. So we were just talking about this plus, minus, maybe I should write this down, this plus, minus 3 standard deviations. So here we're talking about capability. It's referring to the limits of variability. It refers to the variability around a target which a machine or process is capable of producing a particular characteristic. This capability is measured using the standard deviation of the characteristic produced by the machine or process. And in general, as we said, these are going to be the tolerances are going to be plus or minus 3 standard deviations, where T is going to be your target. It's T plus or minus 3 standard deviations. So T is your target, and this is then your your allowed spread around the target. Now, when design engineers choose tolerances, without knowing if the available processes will be able to hold those tolerances, so this could mean that we have a problem. We end up having frustration on the floor because the machines are not able to produce to the tolerances required. And if you require tighter tolerances for the customer, then you need to make sure that you perform, and if it's not capable, you're able to perform a process improvement in order to reduce the output variability before tighter tolerances can be demanded. Now, traditional tolerancing we show here provides an upper and lower specification limit. So here we have we saw capability upper and lower specification limit around a given target. And traditional tolerancing then is based on the premise that the fitness of the product is good only as long as that characteristic is at target or within these two limits. So if this is your characteristic X, as long as you're lying within these two limits, you're okay. If not, you've got a problem. This is your traditional tolerancing model. So, in other words, the losses from the characteristics are zero when you're at the target or within these two limits. Now, we have another way of looking at this. This was Dr. Taguchi, and his model said that that's not true. You only have a zero loss when you are exactly on target and with your characteristic. And the loss will increase, and here we have a parabolic model here, as you move away from your target. Now this is called the Taguchi loss function here, and you can calculate your losses based on this parabolic function. We're not doing this in this course. We're dealing with strict tolerance limits within a certain range, a certain number of standard deviations. But one powerful way of looking at this is to think that just because you're within specifications doesn't necessarily mean it's not as conservative as using the Taguchi loss function, where you actually are considering any loss as long as you're not on target. Now, many situations arrive in industrial settings where assembly tolerance have to be calculated from the component tolerances. For example, if we have a track of a bulldozer is made up of 120 links, so we could write this down, a bulldozer track is 120 links. We may want to know the entire assembly of this my picture of a bulldozer track, of the entire bulldozer track. What tolerances does this assembly have to meet? Another example would be finding the tolerance on the clearance between a bore and a shaft. So we're given a shaft and a bore, and we need to know what is the tolerance then of the gap if we're given the tolerances of the bore and the tolerances of the overall shaft. So in situations like these, we need the tolerance of the total or of the difference of certain characteristics. We can use what's called the root sum of squares formula. So suppose we have L1, L2, L3 up to Ln. So I have to draw this again here. We have components like this, different lengths maybe, L1, L2, L3, L4. And we're interested then in the tolerance of the overall L. I'm writing here L total. So now one thing that's important is that all the components are independent. meaning that the length of one doesn't affect the length of the other in this example. And we have then the overall assembly measurement is going to be simply the sum of all the different components. So now if we're given that T are the tolerances, so T1, T2, T3 are the tolerances of the individual measurements, then the tolerance on the total assembly is given by each one of these individual tolerances squared, and then the square roots. We have to sum them all. Now, this is based on the results for the distribution of the sum of normal random variables. So if one random variable, so your first length, is distributed with a mean and a variance, so standard deviation squared, and your second component, for example, the length has a mean and a standard deviation squared, a variance, then, and if these two are independent, then the sum of these variables is going to be normally distributed with a mean equal to the sum of the means and the variances equal to the sum of the variances. And likewise, the difference between these two variables is going to be the difference between the means, is going to be a normally distributed random variable, where the mean is the difference between the means and the variation. Now, this is not a typo. The variation is the sum of the individual variation. So in other words, even if you're subtracting your random variables, the variances add, the variability add, and this can be applied to any number of independent normally distributed variables. So like if we look at this again, so here we have L1 and L2, and you are using those two components here to make a final component of length L. If these both have a tolerance, so here you have L2 has a small tolerance this way, and L1 has a small tolerance around here. These tolerances are given by TL1 and TL2. Then the overall tolerance is the square root of these two tolerances squared. And the same thing is if you are looking at, for example, here is what we're looking for, this gap. We have L1 is the total length, and L2 is call it the bore, for example. This was the shaft. And then you're interested in what is the tolerance on L. So L is equal to L1 minus L2. They're independent. Again, you find that the overall tolerance for this L gap here is going to be the sum of the two component tolerances. It's going to be the square root of the sum of the two component tolerances squared.